This video is a follow-up from our last video where we started looking at evaluating the basicity of different amines, where in each case what we did was reacted the amine with an acid, and then we compared the stabilities of the conjugate acid products, knowing that the more stable the conjugate acid product, where we reacted a base amine with an acid to give the amine salt, what we saw was that the stronger the base that we started with, the weaker, more stable the amine salt product was. And so we use that as a way of determining how basic different amine groups are. And we are going to continue that here by working through a couple of additional practice problems. So let's take a look. And as always with these, I encourage you to, after we have the problem, hit the pause button, try to solve it on your own, and then use the video to check your work for this to make sure that we're all on the same page. So in this problem, we have a single molecule that has two different amine groups. Here and here, we're reacting with HCl and we're asking what the product of the reaction would be. So in order to determine the product of this acid-base reaction, we're reacting a 1-to-1 ratio of these two reactants. We have to decide which is going to give the more stable product, placing the proton from the acid-base reaction on the nitrogen here, or placing it on the nitrogen atom here. So we have two possible products as a result of this reaction. We're going to decide which one is the real deal. So our two hypothetical products, of which we are going to pick one as our real predicted product. We're making our hypothesis at the moment and trying to sort out and scribble out our scratch paper here about what's actually going to be happening, is that the nitrogen on the left of our primary amines could become NH3 by picking up a proton from the acid. That's going to put the positive charge on the nitrogen. We go ahead and draw out the rest of our group here. Nitrogen here would still be NH, like so, with no formal charge on it. Or, alternatively, the other possible product is that we leave that nitrogen at the far left alone. In other words, leave the primary amine unreacted. And instead, we react that nitrogen that is part of our ring. So our nitrogen that was part of the ring started off as an NH group. By picking up a proton, it becomes NH2+. And then we ask, which of these is more stable? Because the more stable the conjugate acid product, the more favorable it's going to be. So which of these is more stable? The more stable is going to be the more favorable one, because these acid-base reactions are driven by thermodynamic factors, meaning the stability of the final product is what's going to drive what the outcome is. And so looking at these two structures, we ask ourselves, which of these is going to be more stable? And the factors that we consider are resonance, aromaticity, and aromaticity is super important if present. It's not present in a majority of scenarios that we'll come across. But aromaticity, if that's going to be a factor, that will even be more important than resonance generally in determining the stability. And then the third factor is we look at induction and whether induction is going to stabilize or destabilize the products of this. And induction is less important than aromaticity or resonance. So, and I'm going to make an annotation here just to remind you in the future that aromaticity is generally the most important of all if it's present. So looking at these hypothetical products, we have to ask which of these two is more stable. Now looking at them and keeping in mind that business that we were just talking about aromaticity, what we see is that if we recall the guidelines for aromaticity, that they have a Huckel number of 2p electrons around the ring, we would see that the structure up top here, where we have a lone pair of electrons in the nitrogen there, and then we have that conjugated around the ring, this would represent an aromatic molecule. And so, with that representing an aromatic molecule, that's going to make that very, very stable. On the other hand, if we come down to this product where we have NH2+, there is no aromaticity here because the nitrogen now is an sp3 nitrogen, not sp2. And so by resonance, there is no way for that to participate in the electron delocalization around the ring, and there's no way for that to be aromatic. So this is not aromatic. And as a result, this product down below is going to be the less stable of the two products. The one up top is going to be the more stable of the two products because it retains the aromaticity of that ring. And since aromaticity is a huge determining factor of stability, we are going to go ahead and assess that the actual product of the reaction is the one up top here. So we'll predict the product again of this reaction where we again deal with a structure that has multiple nitrogen atoms within the ring. So let's go ahead and draw this out here. Put my NH group in, pi bond, like so. And now that we have drawn that out, we're going to react it with one equivalent of HCl. And we're going to ask what the major organic product would be of that reaction. So thinking about the possibilities here, both of our nitrogen atoms have a lone pair of electrons here and here. And so as a result, we could place a proton at either of those two positions. And so our two possible products would correspond to placing the proton either down here, which would take that NH and move it on up to NH2+, leaving the other nitrogen unmarked, unreacted. Or we could react that nitrogen up top here, leave the other nitrogen unreacted, so that would remain NH. And we would go like so and put a positive charge here. So now we have to ask which of these two structures is more stable. So we ask which of those two structures is more stable by evaluating those same themes that we did before, which is we looked at for each of them, we evaluated the aromaticity, where aromaticity was even more important than resonance. We evaluated the resonance and we evaluated the induction. And if aromaticity is present, that's the most important, second most important resonance, third most important induction. So taking a look at these, is the top molecule aromatic? So remember that we have to have a continuous sp2 system for a molecule to be aromatic. That was one of the criteria. We have a nitrogen atom here, which is sp3 because it has 4 different groups bonded to it. It has 2 hydrogens and 2 carbons. So that's sp3, and therefore, if you have any sp3 atoms in the ring, it cannot be aromatic. So game over for this one on being aromatic. What about the other one? So we come down to here. All right, the nitrogen here, we could create a resonance structure where where the lone pair electrons could become a pi bond to make that nitrogen sp2. And then we look at the carbon atoms are all sp2 already. Our nitrogen here, what's the hybridization of state of that? Well, it has 3 regions of electron density because it has the region going toward the pi bond, the hydrogen, and the other carbon that's connected there with a single bond. So with 3 regions of electron density, it would have an sp2 hybridization. Hence, it is qualified for aromaticity, assuming that we meet Huckel's number. So to look at whether we meet Huckel's number or not, we count 2 pi electrons here from the pi bond, 2 pi electrons here from the other pi bond, and we also count those allylic lone pair electrons. They're allylic to this pi bond over here, or for that matter, the other one, since by resonance, those can come down and participate in pi bonding. So we have 6 of those 2p or pi electrons, and 6 is a Huckel number, and therefore, this structure is indeed aromatic. And so comparing the stabilities of these two molecules, it is now no contest. The one on the bottom is far more stable and hence the major product of this reaction. So to conclude, now that we have done several different examples of reacting amine bases with acids, we should be comfortable in comparing the relative basicities of amine groups within two different molecules, or the different basicities of two different amine groups within the same molecule, so that we can do things like predict what the actual product would be of reacting that amine with an acid. And this is a super relevant concept because, as we brought up a bit earlier, amine salts are very commonly found in drug molecules and a variety of other consumer products because they improve the water solubility of amines. So you will very commonly see reactions where amines have been brought in and reacted with strong acids.